will talk about the 2D anisotropic Kpc equation as stationarity. And the work I will talk about, that's joint work with Giuseppe Canizzaro from Warwick University and Fabio Toninelli from Vienna University. And it's based on some slightly older work with Philipp Schönbauer. Okay, so to introduce the Kpc equation, maybe some of you may know it, some of you might not know it. So let's start with something hopefully everybody knows. So one of the first big results we get to know in our first course of probability theory is the central limit theory, right? So essentially in the first course you learn the law of large numbers and the central limit theory. And the central limit theory really says that, well, if you take a bunch of random variables under fairly general conditions, that probably rescaled sum converges to a Gaussian distribution, to a normal distribution. So that's kind of the first time that you see the Gaussian universality appearing. And then, well, maybe in the second course of probability theory, you push this even a little bit further, because what you're doing, actually, you're looking at random functions, at random trajectories, or in other words, is at random walks. So if you rescale random walks appropriately, under fairly general conditions, well, they converge to Brownian motion, which is nothing else than a Gaussian process indexed by time. So you went one step further, one level further. So you go from some kind of a random variable, which is Gaussian distribution, to a process indexed by time, which is the Gaussian distribution. And well, even if you go to the level of particle systems, which are indexed by space and time, you kind of observe the same phenomena. So again, the Gaussian universality class pops up. And so I would like to give a small example for that, because it allows me nicely to introduce the Kpc equation. So what do I mean with particle system? Well, it's a very general term, but the example, for instance, I have in mind is what people call the exclusion process. So what is the exclusion process? So imagine you're on the d-dimensional lattice, yeah? And at time 0, you start with a bunch of random walks. So now this bunch of random walks along the lattice ZD, essentially independent of each other. Yeah? However, they respect the exclusion rule. So the exclusion rule means that two particles are never allowed to be at the same site at the same time. So in a sense, only if two particles, two random walks, are close to each other, they feel each other. Otherwise, they kind of behave independently. Yeah. So just to clarify it, so let's draw a one-dimensional picture. So in one dimension, it would be something like this. So you start with a certain initial configuration. So at some points of the one-dimensional line, there's no particle, which is drawn by a hole here. And maybe here you have a particle. Maybe you have a particle here times 0. Maybe you have a particle here times 0, but maybe there's no particle here, and maybe there's a particle here. And so let's assume, just for this example, that we think of nearest neighbor random walks. Let's say simple random walks. So what is then really happening? So if we focus now on this particle here, so this particle will look to the left, will look at this edge, will look to the right, will look to this edge. Yeah? And imagine that to each of these two edges, an exponential clock is attached. Let's say of rate 1. So then it waits until one of these two exponential clock rings and will jump. That's what a random walk does. So let's assume that the edge to the left rings first. So this would be this edge. So what the guy will do, he will jump to the left. So then you would have a particle here. Hopefully it works more or less. And there would be no particle here anymore. Okay. There would be no particle here anymore. So this guy jumped. So this guy now does the same, right? So it will look to the exponential clock attached to the edge to the left. It will look to the exponential clock attached to the edge to the right. And when one of the two clocks rings, it will try to jump. So let's now assume that the exponential clock attached to the edge to the right rings first. So what this guy would like to do, would like to jump here, but the exclusion rule prohibits this jump. So in this way, you kind of create a little bit of dependency between these different random walks. Okay. So for what comes now, I mean, the exclusion process I will denote by eta, right? And so at each time t, so what is eta? Well, so it will associate to each side of ZD, it will associate a number, 0, 1, 2, 3, and, of course, this would be also correct, but it's not really standard. So to each side of ZD, it will associate the number 0 or 1. 0 means there's no particle, and 1 that means there's a particle. So one thing that we know about the sky is that it has an invariant measure, and all the measures that are invariant are product Bernoulli. So if we take the product x and ZD, and we take product Bernoulli measures with some parameter rho, where rho is between, say, strictly between 0 and 1, then this is a class of invariant measures. Of course, if rho is equal to 0, this would also be an invariant measure, but this would simply mean that at time 0 there's no particle whatsoever, nothing would happen, so that's quite boring. Rho equal to 1 would also is also an invariant measure, but if rho is equal to 1, so this means at each point you have a Bernoulli with density 1 with parameter 1, this means that each side has a particle, so the exclusion rule will apply that none of these particles moves. Also quite boring. So somehow the interesting invariant measures are with rho strictly between 0 and 1. Okay. So I hope the definition is more or less clear. So you have this bunch of random walks that are not allowed to jump on top of each other. Well, now we know Donsko's theorem, knowing that one random walk properly rescaled converges to Brownian motion, right, which is the Gaussian process in expect time. So it's not crazy to believe that, well, here again with a bunch of random walks, properly rescaled, that they converge to some kind of mixture of Brownian motion. Again, maybe something Gaussian. And actually, that's exactly what happens. So again, we see some kind of Gaussian universality appearing. And this time on the level of fields. So processes indexed by space and time. Yeah, so let's go slowly over it. So I will denote by eta the exclusion process, define ZD, assume say it has a symmetric transition kernel with some finite second moment, and I assume that it starts from its invariant measure. So then what I do, I take a smooth, compactly supported function f, and I define this function yn. And the statement is that this yn converges to a Gaussian random field, the so-called Ornstein-Uhlenbeck process. Yeah? So what it is actually precisely doesn't matter, it matters as Gaussian. So let's have a look at this yn. So what is this yn? So what do we do? I mean, first of all, so we take the smooth, compactly supported function f, and then so you see, we evaluate f at the point x divided by n. F is a compact support, so let's assume this support is size 1. So this essentially means that x divided by n needs to be smaller or equal than 1, otherwise f would be 0. So x divided by n smaller or equal than 1 essentially means that the number of points we really consider in the sum is of the order n to the d. So actually we really consider n to the d points here, not all of the d. So then this prefactor here, what we really do is we divide by the square root of the number of points that we have in the sum. So that's the classical central limit theorem scale. So further what we do, we speed up time by n squared. That's something that we also know from Donsker, and we do some kind of recentering here. Yeah. So that's kind of a recentered field, diffusively rescaled, and it turns out it converges to something Gaussian. So if you only know these three results, the classical central limit theorem, Donsker's theorem, and maybe a theorem of this type, you might get the impression that, well, the Gaussian universality class is huge, and essentially almost everything must be in it. Everything that's kind of reasonable, right? So in particular, what this means, if we would not change this model slightly, let's say we would perturb the exclusion process just by a little bit, well, I mean, the limit should be again Gaussian, right? So let's do this. So let's perturb this model just a little bit. Yeah. So what turns out, say we're in one dimension now, and I add some slight asymmetry that vanishes as n goes to infinity, actually turns out that it has a dramatic effect. It turns out that the limit is not Gaussian anymore. So, before I comment on this further, so what do I mean with asymmetry of that order? Of order 1 over square root of n. Well, asymmetry of order 1 over square root of n means what? So, remember that in the exclusion process, so we have our particles here, let's say there's a particle here, there's a hole here, there's a hole here, and let's focus on the nearest neighbor case. So I was saying that this guy in the middle looks at the two edges and at the two exponential clocks attached to it. And what I did say is that symmetric really means that they both have the same rate, let's say rate 1. And this guy as well, rate 1. So they both ring at rate 1. So this would be a symmetric situation. Asymmetric means now that, for instance, always to the edge to the right, I add 1 over square root of n. Yeah? And of course, I mean, at least what I would expect naively is that, well, as n grows to infinity, maybe you can couple this perturbed exclusion process with the standard exclusion process, and then you show it has the same limit, Gaussian. But well, it turns out that this is not the case. What this really means is that the Gaussian universality class is really unstable under perturbations. It's very easy to be pushed away from it. Yeah. So what turns out, this is not kind of an artifact of the exclusion process, that it has some kind of peculiar properties that kind of pushes it easily away from the Gaussian universality class, but this actually holds for much, much more models. So actually there are many, many models whose limit is not Gaussian. And what they have in common, the limit is described by the Kpc equation. Okay, so it seems the internet is stuck a little bit. And so the thing I would like to talk about now is about the Kpc equation. I'm not sure if you can see the next slide. Okay, so now maybe you can see it. So the limit of all these particle systems is described by this Kpc equation. And so this is the object I would like to focus on today. So what is this Kpc equation? I mean, first of all, on the left-hand side, we have the time derivative of the function h that we search. And on the right-hand side, we have three terms, right? So we have, on the one hand, the Laplacian. We have the nonlinearity. And we have a noise term. So these are the three terms. Okay. So for the experts here, it's maybe more or less clear what's the effect of the Laplacian. For those that are not experts, so let me explain it. So assume that h looks relatively rough. Maybe looks something like this. Yeah? If you then add a Laplacian to the equation, the Laplacian always has the effect of smoothing out the solution and makes kind of the solution more regular, more smooth. So if you kind of add the Laplacian to the equation, so maybe the solution looks, I don't know, maybe something like this, something like that. Something like this. Yeah? So Laplacian has a smoothing effect, flattens out a little bit the solution. That's the effect of the Laplacian. What else do we have here with Kpc, the noise? So Kpc, I assume it's space-time white noise. So what does it mean? It's Gaussian. I assume that's zero mean, and it has trivial correlation, trivial covariance function. So what do I mean with this? That the expectation of psi at point t x times psi of sy. So this is the Dirac in t of s times the Dirac of x in y. So what this formula really means is a way to picture the space-time white noise is that to each point of space and time, you attach an independent zero mean Gaussian random variable. Yeah? So that's really essentially what it means. And so what is the effect of this for the equation? Well, so let's think about this. I mean, on the one hand, this seems to be a super nice object to work with, at least from a probabilistic point of view, right? Because everything is completely independent. Each Gaussian random variable attached to each space-time point is completely independent. That's great. And well, they're Gaussian, and so we have a lot of experience to work with Gaussians. So from the probabilistic point of view, it's a very nice object because, well, we can do calculations with it. However, what we want to do here, we want to solve an equation. So from an analytical point of view, this object is actually not that nice. Well, why is it not that nice? Well, so you know that a Gaussian random variable can take any value between minus infinity and plus infinity. Will be something between minus and plus infinity. Right? So now if you imagine a very small box in space-time, where the number of space-time boxes you have in a small box is not countable, right? So you have an uncountable collection of Gaussian random variables. Each of them will take a value between minus and plus infinity. Yeah? And since you have uncountable many of them, you will essentially observe any value that is super close to plus infinity and any value that is super close to minus infinity, no matter how small the box is you're looking at. So that's an object that's highly oscillating. So if you think of it as a function, as a smooth function, it's not smooth at all. So actually, so the noise term has the opposite effect to the Laplacian and makes the solution look very rough. Right? So that's the noise term. So it's missing one term is missing the nonlinearity there in the middle. So the nonlinearity, there are two ingredients. So there's the gradient, nabla h. So what does it mean? Well, so remember that if you have a function h, so what is the gradient of h? The gradient of h is a vector that's chosen to the direction of the strongest increase of the function. Goes in the direction of the strongest increase of the function. In other words, nabla h is a function of the slope of h. Yeah, so this is really something that's slope dependent. So that's the nabla h. And Q is a d by d matrix. So in one dimension, Q would be number, can be absorbed into the lambda, but in two and higher dimensions, it's a proper matrix. So kind of it models the way you want to incorporate the slope dependence of the nonlinearity. Okay, so these are the three terms. So I hope that small is clear. So again, so nu is the smoothing mechanism. Yeah? The larger nu, the more important should the Laplacian be, the more smoothing effect we should see. Q is the slope dependence. I just described this. D is the strength of the noise. The larger D, the more important the noise size should become. And lambda is the strength of the nonlinearity. So you see, we have four parameters here to play with. Nu, lambda, Q, and D. So I don't want to play with four parameters. This would be a bit too much. So I will fix two parameters. I will fix nu and I will fix D. Yeah, so I will set them to 1/2 and 1. I mean, the precise values, of course, don't matter. This makes some calculations slightly more pleasant, but it does not really matter. Okay, so I fix nu and D and I will play with lambda and Q. Okay, so that's the equation. And well, when you have an equation, the first thing you want to do, you want to maybe show that it has a solution. And maybe you want to show that it has a unique solution. Right? So there kind of you encounter already the first problem. So what turns out is that even if you ignore for one moment this nonlinearity, for one moment, what turns out is that what you can show is the regularity of H is 1 minus d over 2, actually minus. So this means in dimension 1, H has regularity at most 1/2 minus, so it's 1/2 Felder, or a little bit less than 1/2 Felder, like Brownian motion, right? H just fails to be a function, so it's a 0 minus Felder, yeah? Just fails to be a continuous function. And dimension 3 and higher, where it's super irregular. Okay, so you have this, but well, I mean, we know how to deal with distribution, so this is actually per se not a problem. The problem is then the moment you want to define this nonlinearity. Because I mean, even if you're in dimension 1, so 1 minus d/2 would be 1/2, so the gradient of H should have regularity minus 1/2. So in dimension 1, the gradient of H is regularity 1/2, actually a little bit less, minus 1/2. And there's actually a general statement that says that, well, if you have an object with negative regularity, then there's no canonical way of squaring it. So actually, what Alberto presented some minutes ago actually was more or less also about that. Yeah, so you can interpret it in the same sense. So if you have something with negative regularity, then there's no canonical way of squaring it. So what do I mean with this? I mean, one thing you could do is first you regularize it. Okay, so then everything makes sense, and we know how to compute the square, and in a naive classical sense, there's nothing that can happen really. And then you remove the regularization parameter. What happens when you have negative regularities is that either when you remove the regularization, the sequence diverges, or maybe different subsequences of different limits, and no limit is upper better than any other limit. So this is kind of a problem when you want to prove well-postedness, so that there's no obvious way of how to prove well-postedness. So, I mean, of course, the natural approach is to regularize the equation, then to study the sequence of regularizations, and then you hope something comes up. But that's not easy, actually. Okay. So that's one of the problems, but let's put this problem for one moment aside. I mean, at some point I need to take it into account, but let's put it aside for one moment. So let's assume this equation makes sense in whatever dimension. So what is the question of interest? What do I want to know? Well, what I want to know is I want to understand the large space, large time behavior of the equation. In particular, what I want to understand is the relevance of the nonlinearity. So what I want to do, I want to zoom out in space, and I want to understand how important is the nonlinearity. Why is this a question that makes sense? Well, how did I introduce the Kpc equation? Well, I started with a slight perturbation of the extrusion process, with a slight asymmetry, and then I was saying that in the limit we observe the Kpc equation. Of course, what could happen is that, well, once you want to prove that this slight perturbation converges to something, you do some formal computations, and then your formal computation suggests kind of this Kpc equation with the nonlinearity. But we always saw that this equation actually doesn't make completely sense. So maybe what could be is that the nonlinearity is not really there. It's an artifact of some computations you did, but actually it's not really there. So this could happen. And this is what we would like to understand. So how could you attack this problem? So I mean, what we really want to do, we want to compare it to the linear equation where lambda is equal to 0, or where q is equal to 0, right? So the first thing that we might want to do is to look at scalings, right? I mean, we know it from Brownian motion, a lot of properties of Brownian motion we can deduce from scaling arguments. So let's do the same here. Yeah. So what we will do is we look at this scaling. So time is divided by epsilon squared, space is divided by epsilon, and then I have this funny prefactor here in front. So what's going on here? First of all, observe as epsilon goes to 0, t divided by epsilon squared goes to infinity, x divided by epsilon goes to infinity. So I'm really looking at large space-time scales. So why this funny prefactor in front of this h? Well, this funny prefactor is chosen such that under this scaling, the linear equation, so for the linear equation, h epsilon has the same law as h. So let me repeat. If lambda would be 0, so I'm in the case of the linear equation, in this case, under this scaling, this is the unit scaling under which h epsilon has the same law as h. So this computation we can do. So what happens for the nonlinear equation? For the nonlinear equation, what we can show is that h epsilon satisfies this equation here. I mean, first of all, the first thing we observe is that in front of the Laplacian, there's nothing, no epsilon. In front of the noise, there's no epsilon, yeah, and which is consistent with the thing I just told you that under this scaling, the linear equation is invariant, yeah, because for the linear equation, the nonlinearity doesn't exist. So the only effect we see really is on the nonlinearity. So we have this funny factor epsilon to the d minus 2 over 2. So there's some dimension dependency. So let's try to work this out. So what is this epsilon to the d minus 2 over 2? So let's try to work this out. So d minus 2 over 2, let's try to compute some examples. So if d is equal to 1, so then this is minus 1/2, right? If d is equal to 2, it's 0. And for instance, if d is equal to 3, it's 1/2. If d is equal to 4, it's 1. So it's positive as soon as d is at least 3. So what does this mean? If d is equal to 1, here actually we divide by the square root of epsilon. So as epsilon tends to 0, 1 over square root of epsilon tends to infinity, so the nonlinearity blows up. So this means in one dimension, probably what is true, that on large scales, the nonlinearity becomes more and more and more important. If d is at least 3, then we really multiply with the epsilon to some positive power. So as epsilon tends to 0, this thing tends to 0. So probably what should happen is that on large scales, the nonlinearity loses its importance. And well, dimension 2, actually, it's kind of the marginal case, so we don't know actually. The scaling argument doesn't give a hint. It just gives a hint that something special must happen in dimension 2. Yeah, so again, so just to summarize, so this argument suggests relevance is equal to 1 and irrelevance of the nonlinearity if d is at least 3. So on the mathematical side, this has been partially confirmed. So for d equal to 1, there's this so-called Kpz fixed point, which is supposed to be the large-scale limit of the one-dimensional Kpc equation. It has not been proven that the Kpc equation properly rescale converges to Kpz fixed point. As far as I know, there may be some recent works. I'm not completely sure. But so in dimension 1, so there's the so-called Kpc fixed point, which is non-Gaussian, which kind of confirms this conjecture that d equal 1, the nonlinearity matters. For d at least 3, in the mathematical literature, it has been partially proven that the nonlinearity is not relevant. It has been proven for the case for Q, actually the identity matrix times some small constant. And while dimension 2 is the marginal dimension. Okay, so I would like to focus on this marginal dimension, dimension 2. So let's go see what is known in this dimension 2 and what do the physicists think about it. So there's a conjecture of Wolf from beginnings of the 90s, and he's a physicist. And he conjectured that in dimension 2, actually, there are two regimes to consider. There's the so-called isotropic regime. This is the regime where the determinant is Q positive. Think of the identity matrix. Consider. There's the so-called isotropic regime. This is the regime where the determinant is Q positive. Think of the identity matrix. And in this case, what he conjectures is that there are two model independent exponents, zeta and alpha. So model independent means independent of the precise choice of the matrix Q, such that the variance as time increases and space is fixed grows like t to the 2 zeta as t grows to infinity, where zeta is more or less 0.24. And when we fix time, but we vary space, then the variance grows at x to the x minus y to the 2 alpha, for some alpha which is roughly 0.39. Yeah? So we don't know the precise values, so these are numerical values, but probably there's no closed formula. So why is this interesting? So let's go to the anisotropic regime. So maybe then you see why it's interesting. So the anisotropic regime is the case where the determinant is less or equal than 0. And in this case, Wolf conjectured that actually these two exponents, zeta and alpha, are 0 in the sense that the variance in space and time grow logarithmically. Observe that in particular this case contains the matrix Q equal to 0, so contains the linear case. And indeed, in the linear case, if Q is equal to 0, you can verify these asymptotics. So it's a precise, it's an explicit computation that you can do, and you can verify it. So essentially, what Wolf says is that there are two regimes. Isotropic regime is a regime where the equation on large space time scales is different from the stochastic heat equation, sometimes called Edwards-Wilkinson fixed point. And there's the anisotropic regime, where the equation on large scales has the same behavior as the stochastic heat equation. It's a linear equation. So stochastic heat equation is the equation where lambda is equal to 0, Q is equal to 0. Okay, so this is kind of conjectured on the physicist side. So what is known the math side? Let's say starting with the isotropic regime. In the isotropic regime on the math side, the only case we really know how to handle, to say something about it, is the case with Q is the identity matrix. If Q is the identity matrix, then the nonlinearity is simply the Euclidean norm squared of the gradient. Yeah? So this case makes sense to look at this equation, and well, now I need to be a bit more rigorous. So I replace C by a smooth version of it. So phi epsilon is a modifier. So essentially you start with some kind of smooth, compactly supported function phi that integrates to 1. Then you kind of rescale it appropriately, such that as epsilon tends to 0, phi epsilon approximates the Dirac delta. So what turns out if you convolve this with psi? So this convolved object is perfectly smooth and converges to psi. Yeah? So that's the reasonable approximation of the limiting equation. So you can do this, and so what is known? So the following is known. So what has been done here, the prefactor in front of the nonlinearity is what? Is lambda divided by the square root of log of 1 over epsilon. So what is the square root of log of 1 over epsilon? So log of 1 over epsilon, as epsilon tends to 0, tends to infinity. So really this prefactor here tends to 0. So what I really do here is I look at a sequence of equations where when epsilon goes to 0, the prefactor in front of the nonlinearity goes to 0. So I kind of weaken the effect of the nonlinearity. So what has been shown? If lambda is smaller than some kind of a critical threshold, which is square root of 2 pi, then recentering h epsilon, yeah, it tends to some h epsilon, where h epsilon has been identified. H epsilon satisfies this equation. 1/2 dth epsilon is 1/2 Laplacian h epsilon plus square root of some effective constant times psi. So it's a linear equation. Actually, so h epsilon is a Gaussian, has a Gaussian distribution. So now what it seems is that maybe this is an indication that Wolf wasn't right. That actually in the isotropic regime we still observe Gaussianity. But actually that's not the case. So because what is happening? As lambda converges to lambda hat, which is this square root of 2 pi, what happens is that the constant in front of the noise blows up to infinity. So it turns out that if lambda would be chosen equal to square root of 2 pi, you couldn't write down this equation. So it must be kind of a different object. So something must happen here. Yeah? So something must happen beyond this kind of this linear equation, which is an indicator for Wolf being right. And let me make another comment. I mean, here, what we really do, we multiply the nonlinearity by something that's vanishing. And of course, you might expect, well, if I just choose a sequence that's converging to 0 fast enough, at some point, of course, you lose the effect of the nonlinearity, right? I mean, this nobody can deny. But actually, what they really did, they kind of identified the scale at which you expect the nonlinearity to have a non-trivial effect. Yeah? As soon as lambda is at least square root of 2 pi, even dividing by square root of log of 1 over epsilon, you should see the effect of the nonlinearity. Okay. So the proof makes use of the so-called Kohl-Hopf transformation. So you can define the function u epsilon in this way. Yeah? And you can show that u epsilon satisfies some kind of multiplicative stochastic heat equation, which is nice because there's a so-called Fehling-Katz representation. So you can have kind of an expansion of the solution, and you can make use of it to kind of prove this result. And this actually also why in dimension 3 and higher, the matrix that was always used in the math community, because in this case, we can make use of the Kohl-Hopf transform. Otherwise, well, we don't really know what to do. Okay. So that's the isotropic case. Let's go to the anisotropic case. And so there it was conjectured by Wolf that one should see actually the behavior of the linear equation dominating. But it can, of course, be that he is the only physicist that thought that. But actually, if you check a little bit the literature, so I'm citing here two sources, Halpin, Healy, and Asta, in 92, so they say entirely consistent with Wolff's prediction, an anisotropy that involves a change in sign or the vanishing of one of the nonlinearity parameters includes a very rapid, unrelenting, and nearly immediate crossover to the Edwards-Wilkins fixed point. What do they mean with change in sign or vanishing of one of the nonlinearity parameters? What they think of is that Q is of this form, is lambda 1, lambda 2, 0, 0. So change of sign means that lambda 1 and lambda 2 have different signs. So then in this case, the matrix is a negative determinant, right? The Edwards-Wilkins fixed point is the linear equation. And so also, well, something along the similar lines in some kind of a standard work on circle growth models says that thus if the signs of the two lambdas are opposite, the nonlinearity is irrelevant and the scaling is described as the linear Edwards-Wilkinson equation. So it seems that there's some agreement in the physics literature, at least that's what we thought. And what it really suggests for us mathematicians is really to show that in the anisotropic case, the equation behaves like the linear equation. And well, that's actually what we then try to do. Okay, so let's come to our precise model. So the matrix we choose is Q, which is the diagonal matrix with entries 1 and minus 1. Yeah. So then the equation is of that form. So where you subtract the two derivatives. The first thing is that for this equation, there's simply no Kohl-Hopf transform available. Yeah, so which is really bad news because we really need directly to deal with this equation. We can't transform it to a simple equation, work with a simple equation, then kind of go back. So there's simply no way of doing it. On the other side, this equation has an explicit invariant measure, which we know, which is so-called Gaussian free field. So for those who don't know it, I mean, it doesn't matter. The story is really, the invariant measure is Gaussian, and we really know it. We really know it. It's a Gaussian process with correlations given by the green function of Brownian motion. Known object. Okay. So that's really the equation we look at. And, well, I mean, at some point, you want to deal with a well-defined object. At some point, you need to regularize the equation. And the regularization I would choose is of that form. So first of all, to avoid issues coming from infinity, but that's actually not that important, we restrict ourselves a priori to the torus of size L, where L later goes to infinity. And so the equation is on the right-hand side, you have the Laplacian, you have the noisy psi, and you have this funny N1 of H. So what is N1 of H? N1 of H now is the regularization of the nonlinearity. So how does this work? So here's my N1 of H. So what do? I take my function H and I apply this pi1 to it. What is pi1? Pi1 is cut off in Fourier space. So what does this mean? So this means that pi1 applied to some object W, and if I look at the case Fourier component, so then this pi1 does what? It spits out the case Fourier component of W, provided that the norm of K is smaller or equal than L. Yeah? So in other words, we cut off all the large Fourier components, and that's a way of regularizing it, because in this way you can write H as the finite sum in Fourier space. So this we do, we apply pi1, then we can calculate the derivative. Yes, it's completely well defined. Then we square it. What happens then when you square it? So the object inside the brackets has Fourier components of order at most L. When you square it, you get Fourier components of order 2L. So what we then do again, we can cut them off again. So all the Fourier components of orders larger than L are cut off. Yeah. So that's one way of regularizing, which is very convenient here. And we work in Fourier space. because some of the computations we do are very convenient to do in Fourier space. So the Gaussian free field is a very nice representation for Fourier space. So it's a very nice object to work with. Anyway, so that's what we will look at. And so as now what we try to investigate if as L goes to infinity and as we remove the regularization, we see the same behavior as the stochastic heat equation. No? So we look at some observables and try to compare. So again, so the question is, when I use my usual diffusive scaling H epsilon as L goes to infinity and epsilon to 0, which is equivalent of removing the regularization, do I see the stochastic heat equation? I mean, it would be expected, right, at least from reading through the physics literature. However, the surprising answer, at least to us, was no. Yeah. So a slightly informal version of the theorem is as follows, that for any lambda positive, so as soon as you turn on the nonlinearity, the process H epsilon evolves non-trivial on timescales of order log epsilon to the minus delta. So if you think a little bit about it, as epsilon tends to 0, this object, this number here, goes to 0. So as epsilon goes to 0, H epsilon evolves on shorter and shorter timescales. And this is completely different to the linear equation. Why? Remember, I chose the scaling such that for the linear equation, H epsilon H have the same law. So for the linear equation, H epsilon does not depend on epsilon. So the timescale it lives on is independent of epsilon. So this shows that this anisotropic case and the stochastic heat equation, they're not directly comparable. Another thing we showed is that the correlation for the linear equations is square root of t, so diffusive, right? Diffusive behavior. And here the correlation length actually diverges like square root of t times some log t. Okay. The message is really a logarithmic superdiffusivity. So I don't have much time, so let me just dwell on what I mean with the first paragraph, that the process evolves non-trivially on these timescales. And the way I represent is different from the theorem that we state in the paper, but what I will say is rigorous. So it's a kind of a consequence of the theorem in the paper. So non-trivial, for instance, means the following. If you take a test function whose integral is 0, in particular the 0 Fourier mode is 0, which is important because of our invariant measure, these are technicalities. If I look at this kind of a normalized covariance, so what do I look at here? What do I have here? Here I look at the covariance between ht epsilon tested against some test function phi and h0 epsilon tested against some function phi divided by the covariance at time 0, the variance at time 0. So what turns out that there exists some a which does not depend on epsilon, such that for some t which is smaller than this number, this normalized covariance is smaller than a. So now you might think, well, okay, so if I choose t positive, the same thing might also happen for the linear equation, and indeed that's true. For the linear equation, however, the difference is that this a that I have here would depend on epsilon, and if I send epsilon to 0, so this number here tends to 0, so my t tends to 0, a epsilon would tend to 1. But here I'm really bounded away from 1, so somehow for t of order log epsilon to minus delta, immediately I see the correlations of my process evolve. Okay, so I think, the end of my time is there already. So then I would stop here, I think. Thank you very much.